Hello everybody. In this video, we take a look at a problem that deals with steady radial flow to a well. This particular problem includes a confined aquifer. So this one here is the thickness B. The piezometric surface goes from a horizontal line, a horizontal surface, to a cone of depression, like you see in this figure. The difference from an unconfined aquifer is that in an unconfined aquifer, the water surface is actually there, but in a confined aquifer, you'd see water level at any given point in this cone of depression only if you install a piezometric well. So let's level a couple of other variables that we use. The entire height of the piezometric surface from the actually it's measured from the bottom of the aquifer is your H0. The drawdown is obviously the depth to the water, the piezometric surface from the original piezometric surface. And one relationship we need to keep in mind is the drawdown plus height from the datum always equals H0. So with this, let's take a look at the given. We have a constant discharge of 30 cubic meter per hour from the well. We know the aquifer width, we know the diameter of the well. We also know that there is a drawdown of 15 meters at a distance, in the well, which is a distance of 0.15 meters from the center of the well. The drawdown at a distance of 30 meters from the well center is 9.6 meters. With this, we'd like to find out the hydraulic conductivity K for the aquifer. We'd also then like to find the transmissivity, which can be calculated using this relationship. Transmissivity is a product of hydraulic conductivity times the aquifer depth. Finally, the problem is asking us to find the drawdown at a distance of 60 meters from the well center. For which is the color. Okay, for confined aquifer, you can derive the relationship between the flow and the aquifer properties, including the cone of depression. Q equals 2 pi times B K. So this one here equals transmissivity times H0 minus HW divided by log of R0 divided by RW. So in this case, you could get an equivalent relationship just the notations need to be consistent. That's the important part. And this one you can express in terms of h. So h equals hw plus q over 2 pi t times log r over rw. So it doesn't have to be measured at the well. You could measure it at any given observation well. So you could easily replace this to this form. Okay. And using this relationship, we can express this in terms of drawdown. So drawdown at any given point is going to be h naught minus this value. So we could subtract this entire thing from h naught. So that would give us S equals S observed plus Q over 2 pi T log R observed divided by R. So you'll notice this will change position. Okay, so with that equation, S equals S observed plus Q over 2 pi T log R observed divided by R. Okay, so so in this case, we'll call that SW and this one RW. So we'll get 15 meters equals 9.6 meters plus 30 meter cube per hour divided by 2 pi times T. So first let's calculate K. So we can express that in terms of K times B, which is 10 meters times log R observed. Let me just keep that consistent. 30 meters divided by 0.15 meter. Okay, so you can simplify, rearrange, and then solve for K. So this one you get 5.4 times K times 2 pi times 10 . So this equals log 30 divided by 0.15, and you can solve for K, and I'll give you a K of 0.4685 as units of meter per hour. And this You can divide it by 3600 to get K in meter per second. That will be 0.00013 meter per second. Once you get hydraulic conductivity, then we can find the transmissivity. Transmissivity is K times V, product of hydraulic conductivity and the aquifer thickness, 0.00013 meter per second times 10 meters. That is 0.0013 meters squared per second. Finally, we'd like to find out what the drawdown is at a distance of 60 meters from the well center. So we'll start with the same equation we used in the first part. Drawdown equals, so we can use subscript 60 as observed plus, well, we know Q 30 meter cubed per hour, and let's put the value for the drawdown, which is equals 9.6 meters at a distance of 30 meters from the well center, 2 pi. So transmissivity was 0.4685 meter per second times 10 meters. Actually it was per hour, so this way the units are consistent. If we use per second here, we need to make sure our discharge is also in meter per cubic meter per second. Log 30 divided by 60, so the meters cancel out. So with this we can get our drawdown at a distance of 60 meters, and this will come out to 8.89 meters. And one thing to keep in mind is here we can easily replace this pair of drawdown and the distance where that drawdown occurs to the drawdown at the well itself. So I could have used the 15 meter drawdown at 0.15 meter and still get the same answer. Alright, so that is all for this video. I'll see you guys in the next one.